solution A contains the compound copper with 6 waters and then 2 chloride ions. Now, you have to really think about what's going on here because this is not being given to us in the easiest way to understand. But if we remember for transition metals, I'm not going to draw the actual wedges and dashes here, but that we've got these 6 water ligands attached to the copper in a complex ion. And actually with the chlorides outside the bracket, this is a 2+, and then we've got 2 Cl- floating around outside. The first thing it asks us is, what's the type of bond between the oxygens and the hydrogens? I think it's trying to confuse you into saying coordinate bonds, because you know this is a complex ion. But actually, the oxygens and the hydrogens are inside the water molecules, and the water molecules are covalent molecules. So it's just a covalent bond. State why the chloride ions in this compound are not ligands. Well, for them to be ligands, they would have to be using a lone pair to create a coordinate bond to the copper, and they're actually sitting outside of the complex ion as the counter ion, so they're not forming coordinate bonds. So they're not using a lone pair to form a coordinate bond to Cu2+. They could do that, but in this example, they're not doing that. And then it says an excess of ammonia was added. An excess of ammonia was added to the sample of solution A to form solution B. Write an ionic equation. So solution A contains the hexaaqua copper 2 ion. So we can get rid of the chloride ions at this point. And it's going to react with ammonia. Now this is one of those that you have to just remember. It does something different to other transition metals. It replaces 4 of the waters and it leaves 2 behind. So it stays octahedral, but it doesn't replace all 6. And the colour, it's that lovely deep blue colour you get from the ammoniacal version, the compound with the ammonia in. This is kind of testing your knowledge of the required practical 11, the aqueous ions test, because there it says sodium carbonate, remember it's our carbonate ions, were added to another sample. Now because this is a 2+ ion, they're not acidic enough to make the hydroxide precipitates. So what they do is they just make the carbonates. So that we are just going to write copper carbonate or the words copper carbonate if we can't remember the formula. Then it says reagent D was added to another sample of solution A and we got a yellow-green solution. That's given us a clue to the CuCl4 2- complex ion. So what reagent would give us those chloride ions as a ligand? We need to use hydrochloric acid, and then we're going to give that equation, and in this example all 6 water ligands are replaced for 4 chloride ligands. So the shape changes from octahedral to tetrahedral, the bond angle changes. Notice that the charge on the bracket changes because chlorides are negative ligands and water is neutral. So there's a lot going on there for you to make sure you include. And then the last little bit of the question says, explain why colorimetry could not be used to determine the concentration of this compound. So if we have a look at this compound, for colorimetry to be used, it needs to be coloured. So why wouldn't this be coloured? If we look, the copper, if each chloride ion is -1, and this adds up, this equals -1, then the copper must be +1. Now, Cu1+, it has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. And if you remember, the end of copper goes 3d10, 4s1, so it would be 3d10. So it has a full 3d subshell. And to be coloured, you need to have a partially full. You need to have electrons in your 3d subshell, but it needs to be partially full so that they can absorb frequencies of visible light. And that is the end of our question.